Hello everyone, welcome to this week's Crunch seminar. Today we have one talk. So it's on randomized greedy algorithms for neural network optimization in solving PDEs from Xiaofeng Xu. Xiaofeng obtained his PhD in applied mathematics and computational science from King Abdullah University of Science and Technology under the supervision of Professor Jinzhao Xu. He is currently a postdoctoral researcher at Pennsylvania State University. His research lies at the intersection of numerical methods for partial differential equations and modern machine learning approaches, with a particular focus on developing efficient and provable convergent training algorithms for neural networks in numerical PDEs. Xiaofeng received his bachelor's degree in mathematics and computer science with first class honors from the Hong Kong University of Science and Technology and his master's degree from Penn State. With this short introduction, I invite Xiaofeng to present his work.
Right. Thank you very much for the introduction. So today I will talk about the randomized greedy algorithm or for neural network optimization in solving PDEs. And so in this talk, I will try to explain why people want to use neural networks to solve partial differential equation and how do we use neural networks for PDEs. And in particular, I will talk about the challenges in the neural network optimization in numerical PDEs. And that is when the greedy algorithms comes in. In particular, the orthogonal greedy algorithm. I will prove that the orthogonal greedy algorithm achieves the optimal approximation rate for ReLUᵏ shallow neural network. And I will also demonstrate through various numerical experiments to validate the convergence. And finally, I'll make a conclusion and point out some future directions that I will explore. So let me begin with a quick review of different formulations of PDEs. So taking the Poisson equation as an example, we have the strong form. And we also have the variational form, that is to find this function u in h10 such that it satisfies this AUV is equal to FV, where this AUV, the bilinear form, is given by the inner product of the gradient u and gradient v. And also, we also have the energy minimization form. So these three formulations, under appropriate regularity assumptions, they are equivalent, meaning that they admit the unique solution. So by solving a PDE, we can just solve any one of them. So in fact, many partial differential equations admit an energy minimization formulation, and here are some examples. So here are some linear examples: the L2 minimization problem, the Newman problem, or some higher order elliptic partial differential equations. They admit a different energy with a different bilinear form. And we can also have some nonlinear examples. For example, the Poisson-Boltzmann equation have this energy functional. Therefore, we can think of solving a partial differential equation as minimizing an energy functional. So in the finite element method, we are minimizing energy functional on the finite elements function space. And in the neural network method that we will discuss, in particular, we have the finite neural method. Essentially, we are minimizing this kind of energy functional on the neural network function space. And similarly, for the physics-informed neural network, we are also minimizing an energy functional over the neural network function space. So we will be looking at, in particular, the shallow neural network. So although deep neural networks, they could be more expressive. The shallow neural network, they are of simpler structure and mathematically more tractable. And they are also rich enough to approximate solution of partial differential equation, yet the optimization challenge still remains. So therefore, we look at the shallow neural network. So a shallow neural network with n neurons is of this form. So this sigma omega I x plus bi, the in blue is neurons. So it's a linear combination of the neurons. And we can also interpret the shallow neural network as a linear combination of nonlinear atoms from a dictionary. And let me take the ReLU K shallow neural network as an example. Sigma now is the ReLU K activation function. So sigma K, okay. And then the ReLU K dictionary is given by this set that consists of the ReLU K neurons. Here, I want to point out that due to the homogeneity property of the ReLUᵏ activation function, we can restrict the parameters on the unit sphere in RD plus 1. So instead of dealing with the whole Euclidean space, we could restrict it to a compact parameter space, SD. Then this is the ReLUᵏ dictionary. Then the ReLUᵏ shallow neural network function class is given by the sigma n capital M, which is a linear combination of the dictionary elements DIs. They are from the ReLUᵏ dictionary and with a bounded little L1 coefficient. So this is the ReLUᵏ shallow neural network function class that we will be looking at. So let's look at the approximation rate for this ReLUᵏ shallow neural network. And for that, we need to introduce the so-called variation space. So the variation space with respect to the ReLUᵏ dictionary is defined as a set of L2 functions with a bounded variation norm. This is the variation norm. And the variation norm here, we define it as it is defined as the smallest radius of the variation of a scaled variation ball that contains this function. So the smallest radius. That is the variation norm. And this B1D is so-called the variation ball, which is defined as the HM closure of the convex and symmetric hull of the ReLUᵏ dictionary. So this is the variation ball. So it is for the functions in the variation space that we are able to approximate it with ReLUᵏ shallow neural network with the following rate. And what's remarkable about this rate is that it contains the part that is independent of the dimension. This is a 1/2 here. And the other part depends on the kth order of the ReLU and also the Sobolev norm HM and the dimension. And because of this dimension-independent rate, and that is actually why the neural networks are, it is very tempting to use neural networks to approximate a solution of a partial differential equation because of this dimension-independent rate, which is not observed in the traditional finite element method. So we have talked about how to use the neural network to solve a partial differential equation, and we also talked about the approximation rate. So let's look at the optimization problem. So thanks to the energy minimization form, now we can think of solving a partial differential equation using neural networks as minimizing this energy functional among the neural network function space, in particular among the shallow ReLUᵏ shallow neural network function space. And in terms of the parameters, the optimization problem becomes we want to minimize this energy functional by finding the optimal parameters theta, which collectively denoted as A, which are the linear layer parameters of the ReLUᵏ shallow neural network, and omega and B, they are the nonlinear layer parameters for the ReLUᵏ shallow neural network. So this is the optimization problem. Here I want to point out one thing is that if we look at the energy functional, if we optimize over the function space, then this energy functional could be convex. And however, if we look at the optimization problem in terms of the parameter space, because of these nonlinear layer parameters, this optimization problem actually becomes very non-convex. It becomes non-convex and nonlinear. So it is a very challenging problem to solve. So I want to show two examples to illustrate the difficulty of solving this optimization problem. Let's look at the L2 minimization problem as an example. So we want to fit this, do an L2 minimization for the target function u. In this case, I choose u to be this target function. So it is quite oscillatory. And the numerical result shows that the error is very large. So it does not converge when we increase the neural numbers, and not to mention any convergence order. So the error doesn't decrease much. So in this case, we show also I have trained it for a lot of epochs. So in this case, it turns out that Adam fails to converge reliably. So let me show you another example. In this case, the target function is quite a simple function. So it's sine 2 pi x. In this case, we do observe that the error decreases as we increase the number of neurons. However, when we look at the convergence order, it's not the optimal convergence order that we expect. And in the case of 1D with ReLUᵏ shallow neural network, we are expecting a convergence order of 2 as promised by the theorem I showed before. So the message here is that even for very simple smooth functions, we still do not observe the theoretically guaranteed approximation rate with this gradient descent type of methods that like Adam that I used for these two experiments. So in fact, there has been many different training algorithm that has been developed under different contexts, and they could also be used to solve partial differential equations. So here are some representatives of them. So, however, the observations is that these methods, they usually yields very reasonable accuracy in some cases. The limitation, however, is the convergence rate. We want to look at the convergence rate. So the convergence rate, yeah.
Did you try to use a second order optimizer?
No, not for this exam. No, I haven't.
Because it seems to me that's the answer.
Oh, yeah, I should try. Mm, yeah.
But anyway, keep going.
Okay, yeah. So the problem is the convergence rate in practice doesn't match the theoretical approximation rate. And for these methods, they don't have a provable convergence guarantee. Oh, maybe here I also briefly mentioned this neuron-wise parallel subspace correction method that we developed during as our first attempt for this problem. In fact, in this method, we separate the training from we separate the training of the linear layer and the nonlinear layer because of the ill conditioning of the linear layer problem. And for the linear layer problem, we try to design an iterative solver, and we managed to design a preconditioned iterative solver in the 1D case. And for the nonlinear layer parameters, we actually propose to use a neuron-wise subspace correction optimization strategy. And in the neuron-wise solver, we used we used a Gauss-Newton type of method. But still, we were in terms of the convergence rate, we didn't observe that it indeed gives us better accuracy, but in terms of convergence rate, it doesn't quite match with the theoretical approximation rate. Excuse me. So the contribution of this work is we develop a provably convergent greedy algorithm for the ReLUᵏ shallow neural network. And then we also established an optimal convergence rate for the orthogonal and weak orthogonal greedy algorithm under the setting of a convex energy minimization. And in addition, we propose a practical randomized orthogonal greedy algorithm that can solve the efficiently solve the argmax subproblem in the greedy algorithm. For this part, I will also discuss in the slides. And we demonstrate that we observe fast convergence and high accuracy of method through many numerical experiments. So let me move on to the greedy algorithm. Okay, excuse me. So we minimize an energy functional E, right? And the greedy algorithm, this is the pure greedy algorithm. It's the earliest greedy algorithm. So we start with the initial guess 0. And then in the greedy algorithm, we have an argmax subproblem. This argmax subproblem, it selects an element from the dictionary so that it maximizes the inner product with the gradient of the energy. Here, the gradient is the variational derivative of the energy evaluated at un minus 1. So this is the argmax subproblem. The greedy algorithm selects an element at nth steps. It selects an element Gn so that this Gn maximizes this inner product. And then to update the solution, the greedy algorithm goes along the negative of the greedy direction Gn and then update the previous iterate. So if we use the function approximation problem as an example, then the variational derivative is just evaluated at un minus 1 is just un minus 1 minus u. And then in this case, the greedy step, the argmax step, it selects from the dictionary D an element that maximizes this inner product. In fact, it maximizes the inner product with respect to the residue in the special case of a function approximation. So with that, you select a greedy element Gn, and then you go along the negative of that greedy direction. So this algorithm is very easy to implement. However, the problem for the pure greedy algorithm is that the convergence is very slow. So recent result shows that the convergence is the rate is only n to the negative 0.182. So there's also the relaxed greedy algorithm that improves the convergence rate. So the relaxed greedy algorithm is the following. Again, we start with the initial guess 0, and then just like before, at the nth iteration, we pick an element Gn so that it maximizes this inner product with respect to the gradient direction. And then instead of just to update the solution, instead of just go along the greedy direction, it takes a relaxed update by taking into account the previous iterate, un minus 1. So this is the relaxed greedy algorithm. Now one can prove that the relaxed greedy algorithm, in terms of the energy error, it achieves a convergence rate of n to the negative 1. So in terms of the error norm, this will be, given if the function is strongly convex, in terms of the error norm, it will be n to the negative half. That would be the convergence rate for the relaxed greedy algorithm. So it is better than the pure greedy algorithm that I showed here. So we are looking at the orthogonal greedy algorithm that further improves the convergence rate. So here's the orthogonal greedy algorithm. And just like before, we select the element Gn that maximizes in the inner product. But to update the solution un, we collect all these greedy elements that are selected at the nth step from G1 to Gn, and we form a subspace Hn. And then the orthogonal greedy algorithm minimizes this energy functional on the subspace Hn at the nth iteration. And this minimization is equivalent to this variational form. So sometimes to get the exact argmax, the maximizer is difficult. So people also have the weak orthogonal greedy algorithm. So the weak orthogonal greedy algorithm, instead of find an element Gn that is the maximizer for this inner product, it find an element Gn that is so that this inner product is greater than or equal to just a fraction of that maximum. So this is a weakened type of a greedy selection. It's the weak orthogonal greedy algorithm. And then to update the solution UN, it's just like the orthogonal greedy algorithm. We have all those greedy selections, and we collect them and form the subspace Hn, and then we minimize the energy functional on that subspace. So this is the weak orthogonal greedy algorithm. So
Sorry, I have a question.
yeah.
Here when we're talking about Gn, is it in any way, like, is the existence guaranteed and the uniqueness as well? Is it unique or it's not, it's not?
Existence, I think, is guaranteed because D is a dictionary, and this ReLUᵏ dictionary is the parameter space is compact, right? So the
Okay.
existence is guaranteed, but I don't uniqueness. Uniqueness is probably not guaranteed.
So I can have, like, say in the the weak greedy algorithm, I can have a lot of values of Gn, which are just a little greater than some fraction of the maximum.
Yeah. Okay. Thank you for asking. Yeah. So let's look at the convergence of this weak orthogonal greedy algorithm. We assume that this energy functional is convex and L-smooth in Hm, and let U in the variation space be the minimizer of this energy functional. Then for the weak orthogonal greedy algorithm, we are able to get this convergence rate for the energy error. So we are able to bound this energy error in terms of those constants, and these are the weak parameters for the weak orthogonal greedy algorithm, and in terms of the variation norm of the function u, and at this rate. If we further assume that this functional is mu strongly convex, and if we further assume that we can achieve in the weak orthogonal greedy algorithm this gamma L, we assume it to be some constant that is within 0 and 1, then we can get the convergence rate in the error norm in terms of these constant, the variation norm, and this rate n to the negative half minus this. And let us record that.
What is K? Can you tell us what is K, little k?
K is ReLUᵏ, the kth power for the ReLUᵏ.
What?
K is by definition in the previous slides, I used the ReLUᵏ throughout.
So you raise it to some power? You raise ReLU to some power, K?
Yeah. We consider ReLUᵏ shallow neural networks.
So the standard ReLU is what? K equals 1.
1, yeah.
Okay.
Yeah, we yeah. So and then let's recall that the approximation rate for this ReLUᵏ shallow neural networks is precisely the same rate, this n to the half minus this. So therefore, this orthogonal greedy algorithm, or the weak orthogonal greedy algorithm, indeed achieves the optimal approximation rate for this ReLUᵏ shallow neural network.
So can you say because earlier you said for the sign, you expect n to the minus 2, right? How do you get that? So K will be, let's say, 1?
Yeah, sure. D is equal to 1, and then
D1, yeah?
and the K is also 1,
Yeah.
and in the L2 minimization, so M is 0. So that would be, so this part would be 2 times 1 plus
Okay.
1, 3 divided by 2. Yeah, that's how I get the 2. Yeah.
So it will be 3/2. Yeah, minus 3/2. Yeah.
Yeah,
Okay.
yeah, yeah.
Yeah. Thank you.
Thank you for asking. Yeah. And now let's give a quick sketch for proving this convergence result of a weak orthogonal greedy algorithm. And for that, we need to I need to introduce the three lemmas. So the first lemma, it connects the maximum inner product over the dictionary to the inner product with respect to a function v in the variation space. And then the second lemma is just a recurrence inequality that we will encounter in the proof. And the third lemma is giving a bound on this quantity, and this quantity is the geometric mean of those of the projection errors, and it bounds this quantity by the metric entropy of this. Here, the metric entropy, I give a definition here, is the metric entropy number for some set in V is defined as the minimum, the smallest radius, so that the set B can be covered by 2 to the n bars of the radius of that radius. So these three lemmas are used in the proof of the convergence of a weak orthogonal greedy algorithm. So in the first step, I'll just give a very quick sketch. In the first step, we need to use the optimality condition and the L smoothness to obtain an energy decay inequality for the energy decay, shown in equation 7 and 17. And then we will need to give a lower bound on this quantity here. We lower bound this quantity by using also optimality and the convexity. We're able to bound it in terms of the energy error. With that, we can write a recurrence relation like this, where A is actually given by the difference in the energy. So this is the energy error. So we have this recurrence relation. And with the recurrence relation, we use the previous lemma, the lemma 2, and we are able to bound this an by 1 over sum of bi's, and by this is from the mean equality. And the point here is that this quantity is given by this. And if we look at the quantity in blue, actually, this quantity is bounded by the metric entropy, as we show in the lemma 3. So this quantity is bounded by this metric entropy, and the metric entropy has this rate n to the half minus this, and thus we complete the proof. So it gives us the same rate as the optimal approximation rate for ReLUᵏ shallow neural network. So this is just a quick sketch for the proof. So we actually still need to, so with the greedy algorithm, we still need to solve, although we have the convergence proof, but there's another challenge in the greedy algorithm, that is the argmax subproblem. So in the argmax subproblem, we need to select a dictionary element Gn so that it maximizes this inner product. And by that, it means we need to find the parameters, the optimal parameters for that neuron, so that it maximizes in this inner product. And again, this is a non-convex problem, and it is very difficult to obtain an exact maximizer. And in practice, we usually use some discretization of this dictionary. And then we maximize over, instead of we maximize on this continuous dictionary, we maximize over a discrete dictionary. And another challenge is usually the size of the discrete dictionary will become so huge in high dimension, and then this argmax problem becomes very computationally costly. So we also propose to use, for that, we propose to use a random discretization. And these type of discretization would actually correspond to a weakened type of greedy selection in the as we show in the weak orthogonal greedy algorithm. So let's talk about how we discretize the dictionary. So this is the ReLUᵏ dictionary with the parameter on the sphere SD, so hypersphere SD. And certainly we could come up with a grid for this sphere. However, to get a deterministic grid on the hypersphere, it is easy for low dimensional S1 and S2, but for high dimension, this becomes non-trivial. So instead of to put a grid, instead of dealing with this hypersphere, we could look at the hyperspherical coordinate map. By using the hyperspherical coordinate map, we can instead look at the hyperrectangle. And then with that, we can reparameterize the dictionary so that the parameter is now in the hyperrectangle. And with the hyperrectangle, we can easily put still it is it is very large, but we can put a hyperrectangular grid on this hyperrectangle. And that is the deterministic discrete dictionary we can construct for this problem. And we propose to use a randomized dictionary. So the randomized dictionary, we could just actually sample from the uniform distribution on this hypersphere. As it turns out that sampling from a uniform distribution on SD is quite standard. We can do that by generating a standard Gaussian vector, and then we normalize the Gaussian vector. That will give us a uniform distribution on the sphere. So to get a randomized discrete dictionary, we could simply random a lot of samples from the uniform distribution on a sphere, and then we get the randomized dictionary. This capital N is the size of the randomized discrete dictionary. Then in the numerical experiment, I will actually compare the randomized discrete using the randomized discrete dictionary and using the deterministic discrete dictionary. I will show that this using the randomized discrete dictionary, it saves us a lot of dictionary elements. So we can use a much fewer dictionary elements in the randomized discrete dictionary. So this will be the final algorithm that is actually implemented, which is the randomized orthogonal greedy algorithm. So at each iteration, in the first step, we first randomly sample this discrete dictionary. By sampling from the uniform distribution on the sphere, we get this randomized discrete dictionary. And then in the next step, we do the greedy selection. So we solve this argmax problem over the discrete dictionary, and then that gives us the greedy selection at the nth iteration, which is Gn. And the last step is after we have all those greedy directions, we form the subspace Hn, and then we solve the minimization problem on that subspace Hn. Or equivalently, this is a variational form. So this is the randomized orthogonal greedy algorithm. Oh, before I go to the numerical experiments, let me also discuss very briefly about the analysis for the discrete dictionary. So the question here is, as I mentioned, if we use a discrete dictionary, then this we go back here. Then instead of getting an actual maximizer, we are getting a maximizer on the discrete dictionary, so which is approximately the actual maximizer. Therefore, using the discrete dictionary can be actually analyzed by the weak orthogonal greedy algorithm, because the weak orthogonal greedy algorithm says that we do not need to find the exact maximizer. We can weaken that condition. So we find an approximate maximizer, but we can still have some convergence. So so this is the analysis for the discrete dictionary. So assuming that we have this GM star, that is the actual maximizer. And this lemma quantifies how close the selected greedy element needs to be, how close this needs to be from the actual maximizer, so that you can still guarantee a weak orthogonal greedy algorithm. And if you can guarantee a weak orthogonal greedy algorithm, then you can still guarantee some convergence. So we are able to quantify that distance in terms of the weak parameters and the Lipschitz constant of the parameterization, and more importantly, the energy error. So this will tell us how fine, if we are using a deterministic discrete dictionary, how fine the grid needs to be, or this can tell us how many samples do we need in order to guarantee that the selected greedy element is actually close enough to the optimal. Okay. So now I'm going to show some numerical experiments. So I did it for L2 minimization problems for the second order elliptic PDE, also a biharmonic equation, and some nonlinear PDEs. And we also explored some indefinite elliptic partial differential equations. Although the indefinite partial differential equation doesn't fall under the framework of the theoretical framework, because in that case we do not have a natural energy minimization form. But I will show that soon. So let's look at the first two examples that we showed. So for this sine 2 pi x with the orthogonal greedy algorithm, now we are able to see very nice convergence. So in the 1D ReLUᵏ, we are able to observe this second order convergence, which matches with the theoretical result. And then even for this oscillatory example, as we increase the number of neurons, we also observe a very good convergence for this ReLUᵏ shallow neural network. So this is a four-dimensional L2 minimization problem. So the target function is a product of sine. And I tested two activation functions, ReLUᵏ1 and ReLUᵏ4. And in this experiment, I want to compare whether using a randomized discrete dictionary is actually better than using a deterministic discrete dictionary. So I tried the randomized discrete dictionary with different dictionary size, 2 to the 6, 2 to the 8, 2 to the 10. And for the deterministic discrete dictionary, I tried other sizes, 2 to the 10, up to 2 to the 14. So let's look at the picture on the left. So first, we see that this blue curve is the reference curve that represents the optimal convergence rate. So first we observe that for the randomized discrete dictionary, we can see it matches with the optimal convergence rate. And for the deterministic dictionary, that is those dotted lines, we see that as we now increase the number of neurons or the iterations, it does not match the optimal convergence rate. And furthermore, we can see that using for the randomized discrete dictionary, we can use a much fewer dictionary size, but we can still achieve a much better convergence result than using the deterministic dictionary. And that's the same for the ReLUᵏ to the fourth power. So from now on, I will use the randomized dictionary, and I will specify the size of the randomized discrete dictionary in each experiment. So this is a 3D Newman problem. with the Newman boundary condition. And the exact solution is the product of a cosine. And we computed the right-hand side. So we have the activation I tried is ReLUᵏ to the third power. And in this example, we only need to use 256 for the size of the randomized discrete dictionary. And we observe a very good convergence order for this problem. And also we have a 4D Newman problem. The target function we choose to be a Gaussian, and we observe very good convergence. Similarly, we can push this to dimension 10, and the solution is chosen to be a Gaussian, and we also observe a very good convergence order. This is the example for the biharmonic equation, and I did it for 2D and 3D. For the biharmonic equation, we can also observe the good convergence order. So this is also, and then this is an example for the nonlinear PDE. In this case, it's a 3D Poisson equation with a, with a cubic nonlinearity. And a very good convergence order is achieved. So we also tried a 3D Poisson-Boltzmann equation. And in this case, I choose the underlying solution to be a Gabor function. And we also observe very good convergence order. So I want to draw your attention to this indefinite. So these are all good. And these previous examples, they fall under the framework of the analysis, because each of them, they have a very, very nice energy. But for the indefinite problem, I considered here, this is a general second order elliptic PDE. The difference is this a convection term. And because of this convection term, this indefinite problem no longer have the energy in the variational sense. But we could still actually modify our orthogonal greedy algorithm so that we can still solve this problem. And the result is also very good. And we also tried this indefinite problem, use the tangent edge activation function. So this experiment is to show that the greedy algorithm, although the theorem is developed for the ReLUᵏ K-shallow neural network, but in practice, the algorithm itself can be extended to other activation functions, like the tangent edge activation function. And we also observe a quite good convergence result. And still, we look at, as I said, for this indefinite problem, we don't have a natural energy in the variational sense, but actually we could also use the energy from the physics inform the neural network. So we can use the ping loss for this two-dimensional, here, this is a two-dimensional convection diffusion equation. And then using under this framework, we naturally have an energy functional. And with that energy functional, we can also apply our orthogonal greedy algorithm, and that also gives us a very good convergence result. Okay, so in conclusion, in this work, I extended the convergence theory of orthogonal greedy algorithm to general convex optimization problem, and I also extended the convergence theory to its weak variance, namely that's weak orthogonal greedy algorithm. I proved that the optimal approximation rate of ReLUᵏ K-shallow neural network can be achieved by the orthogonal greedy algorithm. And for solving the argmax subproblem, I propose to use a randomized discrete dictionary, which improves the practical efficiency of the greedy algorithms. And I also demonstrated order of magnitude reductions in the dictionary size with the proposed randomized strategy. And in summary, I developed a practical and provably convergent greedy solver for neural network optimization in solving PDEs. And here are some of the very brief future plans. For example, for the indefinite problems, maybe I should study the convergence analysis for the orthogonal greedy algorithm, as the experiment is showing some very promising result in terms of convergence. And furthermore, which is more important, is how do we design this greedy algorithm that is convergent for training deep neural networks, and even we can maybe try to use the greedy algorithm to design training algorithms for operator learning. For example, can we come up with a greedy mechanism that trains the deep ONet architecture? And these are some of the things that I'm thinking of doing in the future. And thank you very much for listening to my talk.
Thank you, Xiaofeng, for the great presentation.
Thank
We
you.
can now open the floor for more questions.
Hi, can I ask a question?
Yeah.
Hi, I'm Jamin, a postdoc at Brown, and I'm just wondering, have you tried increasing the number of neurons so that the L2 error becomes Gaussian epsilon?
Oh, that's a very good question. Actually, I want to mention for this method, actually, at this current stage, we are not able to. Yeah, unfortunately, I'm still not able to push this to machine epsilon. Although the theorem could guarantee its convergence, but in practice, there are some other issues, and so that's why actually I for this 1D experiment I think I can push it to 10 to the negative 10, but not further. And let me tell you the problem. The problem is here. So although the algorithm I can prove it convergent, but there are challenges. For example, maybe sorry, let me find the algorithm. Yeah, there are challenges. For example, in this part, in the variational, you need to solve this variational problem on the subspace. And if once the neural number got increased very large, in fact, we know that the condition number, if we use ReLU or ReLUᵏ, the condition number is bad, right? So eventually, this step you cannot get. You must have a very good preconditioner in order for you to push the accuracy to machine epsilon. That is one challenge. That is actually, yeah, we were facing that challenge, and we that's why we were thinking of maybe we should design some precondition. Yeah, but we 1D, I think we managed to push to 10 to the negative 9 or 10 to the negative 10.
All right, thank you so much.
Thank you for raising that. That's very important question. Thank you.
Hi, Xiaofeng. This is Raj from Brown. Can you go back
Hi.
to your slide 25?
Page 25? Yeah.
Yes, indeed.
Okay, yeah, that's the algorithm.
So here, step 7 is kind of you're computing the directional derivative, right? It's inner product.
Yeah,
So if you're sampling Z from a normal distribution or Gaussian, it will be very noisy.
I'm sampling from
Uniform or maybe uniform, because depends on the variation, because if then it will be very noisy, variance of the uniform depending on the distribution, so it will be very noisy if you're just using G for one sample. No, you didn't observe any noise like in the convergence, like
sorry, let me think about.
Do you have any history plots to show us convergence? History of the convergence to show us that maybe?
Yeah, I just this is the plot.
No. We mean the history, no, the history. Oh, this is sorry.
These are the result, right? This is how it converges.
This is with a number of neurons, but I think for fixed number of neurons,
yes.
iterations on the greedy method.
Oh, in the greedy method, like each iteration, we add a neuron. So the number of iterations will be the number of neurons in this.
Oh, okay.
Yeah, it's good. Greedy step. Each time I find a neuron, no, in the greedy algorithm, we construct the neural network by
So then it's pretty fast, right?
which step are you talking about?
Oh, no, I mean, in 500 steps, you sort of converge.
Yeah, that's very fast. It's very fast. 500 or even 1,000 steps. It's very, very fast.
And this is just for one layer, right? This is just for one layer.
Yeah, one layer, one hidden layer shadow neural network.
Yeah. So if you go deeper, I think this will have a lot of noise because we did similar work with randomized forward mode, and we have encountered that issue. Like if you go deeper, your gradient will be very noisy, and it hinders the convergence.
Actually, it's currently not clear how do you design this type of
Yeah,
greedy
so
algorithm.
what we do, this G is sampled from certain distribution from where the parameters are sampled for neural network. And then you just compute the directional derivative like you did in 7, and that gradient will give you the update gradient for the updating the parameters. So that's very simple approach, but if you look at the higher order moments of error, then you will see that how it is bounded by the noise of the noise or variance of the distribution.
Oh, okay. Oh,
Yeah,
thank
so
you.
that's yeah.
I think I haven't thought
Yeah,
about that.
let me put the paper. It's very similar to what we did actually. Let me put the paper.
Oh,
It's
that would be
about
great.
to appear in SIAM Data Science, but yeah.
Yeah, if you could share the paper, that would be
And
great.
also, just one question: did you look into higher order of moments for the error? Like you just because the error you have shown this the first order moment, right? So have you looked into the higher order of the moments for the error for this?
Higher. Sorry, I didn't quite. I think I didn't quite understand. What do you
Okay,
mean
that's
by
fine.
high order errors?
The square of the error, if you just look at the square of the error, the higher order of the moment.
Oh, why do we?
Because
No, I
sometimes,
just look at the L2 error or the H1 seminorm, H1 seminorm error.
okay, so because the distribution affects the effect of distribution comes when you go for higher order moments, what we observed actually. So just was
Oh,
wondering that if you have looked into that. So
uh, I see. I think I didn't look at the.
okay, I just put the paper, maybe you can look at it.
Okay, great. Thank you.
Xiaofeng, can you show us the results of pins again? Sorry,
Yeah.
Suku. I will just finish.
This slide, yeah.
Yeah. How come in let's see, the order for the L2 is 1.36, H1 is, oh, I see. So it should be like twice, right?
Oh,
No, you have a lot. No, it's fine. I misread, but the order of the loss is related to the order of the error.
uh,
Maybe not.
yeah, like here. Yeah.
There's a little bit of an inconsistency because, for example, if you look at the L2 error 1.89, 130, then 2.62, the loss. But then when it gets to lower error in order, the loss order is higher. So I don't know. If you look at the last two lines.
Like here, I see.
Yeah.
I think it's probably it comes from the randomized dictionary. Each step we randomly sample the dictionary, so they will have I think, yeah.
Not the fact that it's non-monotonic, the fact that the loss order doesn't agree with the error order. That's what I'm asking.
So the loss order is I think it is different from the order, for example, in the L2. because the loss is actually marrying this energy. It's the energy error.
Right, but the more accurate the loss, the better the error, right? They're related, positive correlation.
Yeah, the more accurate the loss, the better the error. Yeah.
Which doesn't show that here. Anyway, it's the detail. Maybe you can double check the results.
Okay, yeah, maybe I'll check the detail. But here the error loss is decreasing then. Oh, you mean that this order doesn't quite match, right?
Yeah.
I see. Oh, yeah, I need to check.
Better order in the loss than in the error. It should be consistent, I think. But
I see. Yeah. I see.
Suku has a question.
Yeah,
Maybe
yeah, yeah.
Suku.
So
Hi.
my just observation, or I'm curious why you chose only Neumann problems for all the problems.
Oh, it's the fact is that it's actually easier. It's
Okay.
easier to implement because
So
I can just incorporate this natural boundary condition into the energy.
right, right. So there's no constraint on you, right? So your space is not constrained.
Yeah.
And the other sort of suggestion may be did you also monitor as n is increased, did you also monitor the sort of energy of the numerical solution or the pin solution compared to the exact? Because in all problems you have an exact solution, right? So you know what's the exact energy. So you can figure out how close you are to the exact. So
yeah, I think actually
going back to your slide, I don't know, slide 3, I forgot, where you present the variational formulation.
Let me go back.
Yeah, so if you have so you know E of V, so you know if you have the exact solution, you can compute E of the exact solution.
Yeah.
Right?
Yeah.
And so of course you can compute the E of every U1, U2, your approximation.
Yeah.
So you should monetarily decrease, presumably, right?
Yeah, that is monetar.
Yeah, and you cannot go below the exact, right? So, but the question is, yeah. Yeah. Anyway, just a comment.
I think I didn't put it here, but actually, for some of the experiments, we have this the theorem. If you look at the convergence theorem, yeah, so I was mainly looking at the L2 errors or the H1 errors. But if you look at the convergence result, actually, you are saying this right? This should decrease, and actually, the energy should decrease at the rate like double the rate of the error.
Yeah. But I just wanted curious how close you were to the exact. I was wondering as you decrease, right? Because if you're very close, then you know pretty much you have to be accurate, right? Overall, right? But compared. So what's the difference between UN minus U versus E of UN minus EU, right? There may be, there'll be some correlation in that, but yeah. Okay. Thanks.
Okay. Right. Thank you for asking.
Do we have any further questions for Xiaofeng?
Hi, I had a quick question. So,
Hi.
by the way, I'm ReLUᵏ. I'm a first year PhD student at Brown. So, you kind of explained that having a randomized discrete dictionary works out better than a deterministic discrete dictionary, right? Like you see that the scaling doesn't show up in the case of the deterministic thing. It saturates immediately after some number of iterations. Could you explain like why is that happening? Is that a empirical observation that you had, or is there some reasoning about why you think that is happening?
I think we do have some understanding. First let me understand your problem. You are saying the first is why the randomized works better than the deterministic, right?
Right. Yeah.
Then the second question is like why indeed the randomized works.
Exactly. Yeah. Both of them are like
the first is
effectively
easier
the same
to
question.
answer. Is it's natural for high dimension. You do the Monte Carlo. This is kind of like the Monte Carlo method actually for doing the argmax, right? The first is easy to answer, but the second actually is very good question. Very good, because actually I skipped this slide. Uh, the bound we have for the size of this randomized dictionary is quite pessimistic. So this is a sufficient bound, but sufficient bound being pessimistic is fine, but it's very pessimistic because it depends on the dimension. So this theorem, this analysis, although is it doesn't quite explain the good performance of the experiments, right? So you wonder why actually uh, why this randomized works. There's an insight. There's some insight we have, but it's after we complete this work. So we can what we can do is for example this problem, right? This problem we can after the random greedy algorithms chooses the parameters. We look at how the parameters are distributed on the sphere, right? We look at the distribution, and it turns out that for some very smooth functions, these neurons they are distributed quite evenly on the sphere. So then, if they are very distributed quite evenly, then randomly sample will likely to give you a good neuron. But another observation is for some functions with singularity, like in the Alencon, you will encounter double well, rather than you have sharp interface. We have that in the paper. We also look at how, for that target function, we look at how the neurons are distributed on the sphere. And then for that, you will see some neurons are more clustered at one region than other regions. So I think so. This is what we found after we come up with this algorithm. And for some very smooth function, actually, the neurons are indeed distributed quite well on the sphere.
Okay, got it. Okay, that's a very interesting insight. So are you saying like the kind of approach that you want to use for the discretization of the dictionary could also be dependent on the PDE that you're trying to solve, depending on the properties of the PDE and the solutions that you have there?
Yeah.
Okay. And finally, I think at the end, when we were talking about advection diffusion kind of equations where you don't have an energy functional that you can minimize, right? So in that, I didn't quite follow. So how do you pose the problem into your framework?
Oh, that's very nice. Oh, that's another good question. First, one way is to use the ping, then we
Right.
have the energy. Another way is actually that's why I didn't put it in the slide. It would be too much. That's why I put this variational formulation here. So
Right.
the algorithm itself doesn't rely on the energy. We could just have the variational form and write out the algorithm. So for the indefinite problem, I still have the variational. I can write the variational form. It just doesn't have the energy. So I still formulate the OGA, the algorithm. But of course, in this case, then the analysis doesn't work. The analysis works on the case when we have an energy, and also when we have an energy that is convex and smooth.
Right.
We can
Okay.
slightly modify this algorithm so that it works for the indefinite one. That's the message.
Yep, thank you. And is one of the future directions also to explore like probably having more layers, or is it intentional to just stick to one layer so that you have more interpretability and more control over the predictions? The structure of the neural network.
Right now, we did only for one layer because
right.
one layer, yeah, indeed is more interpretable, and we have a very good approximation result that can match this. But
Right.
higher, deeper neural networks first. I think if we follow completely the framework here, we need to understand first the rate, right? What's the convergence rate?
Yeah.
Then we try to design the algorithm that try to match the rate. I have the idea. I'm actually working on how the algorithm aspect for training deep neural networks using greedy algorithm. That can be done.
Okay.
That can be done. But the theory, the approximation rate is just not as nice as this one shallow neural network case where we have those two rates that matches precisely.
Got it. So, yeah, thank you.
Thank you for raising these wonderful questions.
Do we have any other questions for Xiaofeng? If not, I would like to thank Xiaofeng again for presenting his work at the Crunch seminars. Thank you all for attending, and I hope everyone have a good weekend. Thank you.
Thank you very much. It's very nice to give a talk and talk with all of you.
Thank you, Xiaofeng.
I really enjoyed the discussion. Okay.
Thank you.
Bye.